Once again, welcome to this course on the quantum mechanics part of PH101. We have been talking about uh, the quantum ideas that have shaped, the initial days of quantum mechanics and the problems that people face therein in order to explain various results. And one of the things that emerged out towards the end of the discussion in the last outing was that there are experiments involving light, which means a stream of photons, which often show a dual characteristic. And this dual characteristic is called as the wave particle duality. And in some experiments, light shows up as particles, which Newton initially conceived light to be having a particle nature because they get reflected from a shiny surface. And in some other experiments, they show up as waves such as interference, diffraction, and so on and so forth. Okay, so this had to be reconciled, that whether light is really a particle or a wave. And not only light, there are more massive particles such as electrons and neutrons, which also show similar wave particle duality. So it is seen not only in photons but also in matter waves. And so de Broglie reconciled this and said that there is the duality is real, and one can solve it by saying the wavelength of the wave associated with a particle is it does obey a relationship with the momentum of the particle, which is given by lambda equal to h over p, where h is the Planck's constant, p is the momentum of the particle, and in non-relativistic physics, p is equal to mv. And we are sort of this tells you that every microscopic particle that we talk about has a wave description, and also it has a particle description, and the wave description comes with the lambda, which is the wavelength, which is the distance that it travels over one complete oscillation, and p is the momentum of the particle. Okay, so let us see two very important experiments which have conclusively shown these characters, wave and particle characters of light. And as I said, that we could actually go beyond light and talk about electrons and other more massive particles. Okay, so the two experiments that I'll be talking about, which had shaped the quantum theory in those days, one is the photoelectric effect, and the other is the Compton effect. There are other experiments as well, which I'll not go into, but these are the benchmarking experiments which have been done. So it's not only the experiment and the results that we are going to talk about, but we are going to also talk about how different concepts have been established and how the existing concepts had to be modified and sometimes completely replaced by new ideas. Okay, so we'll start with the photoelectric effect, which you might have seen. And mostly Einstein's name comes up with this photoelectric effect, but Einstein is not the person who actually did this experiment. In fact, it was initially done by somebody called Hertz in probably 1886, 1887, around that time. Okay, let me first draw the apparatus which was used by him. It's a rough schematic of the apparatus and not drawn to scale, of course. So this is a glass, enclosure. So we'll write it as a glass enclosure. This is a quartz plate. Window. I mean, basically, it's a window that is made of quartz. There is a metal target, okay, which is made of, or rather, it has a lot of electrons which can be emitted, and there is a sort of a light comes from here from a source, say for example, okay, and light comes and falls onto this. Electrons eject out from this, and let us say that you have kept so there is a galvanometer there, and this galvanometer, so these electrons, this is just to make sure that the light is passing and not getting obstructed. So this electrons come out from this metal target. So this is the metal target. And this is associated with some kind of a, say for example, well, I mean, this could be here, and this is a variable voltage, and it's very rough and schematic just for you to understand. The metal target could be sodium, or could be graphite, or could be any other metal, and this metal, the light from here could be visible light, say for example, and it goes and impinges on this target, and electrons come out, and they are being collected by this anode, say for example, and this anode is connected to a galvanometer or an ammeter which measures current. So the electrons come out, and because they are coming out by the photons, they are being ejected by the photons. That's why they are called as photoelectric or photoelectrons, and this effect is called as photoelectric effect. Okay. So the two things that I've said is light falls on the metal plate, and the electrons are emitted, which are finally collected by the galvanometer. So this is the experimental setup. So let's talk about the experimental finding. And the experimental finding was like this, that as you make this metal target to be more and more negatively biased, the photoelectrons or the photocurrent that's recorded by the galvanometer, that reduces, and for some negative voltage it goes to 0. So it sort of is like this. I'll tell you why is it saturating. So it goes to 0 like this, and this is called as the stopping potential. Let's call it as V0, and this is the current I that is measured by the galvanometer, and this is the voltage. So this voltage is 0 here. At some negative voltage, the the photo current goes to 0, and it saturates, of course, at large voltage, and for the reason that they are not, I mean, whatever or whatever electrons were there which could come out of the metal target has come out. Okay, so by increasing the voltage infinitely, you won't get any more current. That cannot happen, because there are fixed number of electrons at the target, and it's only that the beam is impinging on a small surface area on this target. So the whatever electrons are there in the vicinity, they come out, and that's why it saturates. But what's more important is that it saturates, but it goes to 0 at some stopping potential which is negative bias, and so at some minus V0 it just goes to 0. And what additionally was found is that this stopping potential V0 is independent of the intensity of the light used. So if you use another intensity of light, let's call it as I1, then the current is I, so let's call it as a current. Let's not mix. So this current, and this is I1 and I2, which are two intensities, and say for example I1 is greater than I2. There's a qualitative difference, or rather quantitative difference between the current. The saturation happens at lower values in terms of the current and so on, but this is same. Okay. Now this is also counterintuitive according to classical ideas and so on and so forth. And all right, so this is the result that one got, and this result was uh, written down in terms of the maximum energy of the photoelectrons which are able to overcome this barrier, and this is written as E V naught, where E is the electronic charge and V is the stopping potential. Okay. So this is the maximum kinetic energy of the electrons which could come out from this stopping potential, and one writes down that this is the relation between the maximum kinetic energy and the stopping potential. Now the K max is found to be independent of the intensity of light. Okay. All right. So let us now do an extension of this, or rather there was an automatic extension of these ideas, and somebody called Milikan, whom you might have heard of, in 1914, he did a lot of experiments with a number of metals, and he tried plotting this stopping potential. Let's call it a stopping potential V naught versus the frequency of the light that is he uses. Okay, and so this is the frequency of the light source, okay, that he uses, and he finds that there is a nice linear dependence, but there is also a cutoff frequency, let's call it a nu c, and this nu c denotes a frequency below which there is no you know there is no current, and there is only, and this beyond nu c, the stopping potential V naught depends linearly on nu. And these experiments were important in those days for the reason that for three reasons. Okay, because one understood that you cannot simply take a particle approach in order to understand, because these there are energy, of course, has to be conserved in the process, and so the abnormalities are the following. Okay, so abnormalities that were found here, by the way, 1925, this Milikan got the Nobel Prize because of this. Okay, 1925 or 23, I'm sorry, this is 1923, and he did on a large number of metals, but for sodium being the metal target there, he got that the stopping potential, or let's write it as nu zero, or this frequency, the cutoff frequency, to be 5.6 into 10 to the power 14 hertz. Okay. So first people tried applying classical wave theory of light, which was very prevalent in those days in terms of electric field and magnetic fields, which were known to be classical waves, classical fields. So if you apply that, there are three abnormalities that were found. One is that the K max should be should be proportional to the intensity, okay, but experimentally it's not, okay, but it is not. Okay. All right. So this is one of the abnormalities that one found. Second is that there should be no cutoff frequency. Which we have called as nu zero. There should have been no, but experimentally there is a cutoff frequency, which is what Milikan saw, and his experiment actually is found to be true for a large variety of metal targets and so on. Okay, but the classical wave theory says that as soon as you shine light on a metal surface, electrons should come out, and it doesn't matter what frequency. So there should be no cutoff frequency. Okay, and the third one is regarding that if you apply classical wave theory to be incident on the metal surface, then it requires some time for the electron to come up, because the electron will have to gather that energy which comes from the energy of the wave, of the light waves. So the energy will be transferred from the light waves to the electrons, and the electrons will come out. So there will be a time lag that should be noted between shining light and recording current, but no time lag is recorded. So it is instant. And this is where Einstein comes in, and he explained this experiment nicely. Let us see that. All right. So what Einstein did was that he took this experiment very carefully, and he said that so this photons of energy E equal to h nu. So he is no longer thinking that light is like a classical wave. So he is buying that oscillator picture which Planck had put forward, that these light is actually made up of small quantum called photons, and these photons have are emitted or absorbed by any surface or any medium in units of these a certain number of these oscillators. Each one has an energy which is given by h nu or h cross omega, whatever you want to call it. Okay, so he said that so a photon of energy E equal to h nu is completely absorbed by an electron, and that's when it comes out. So the kinetic energy of the electrons that comes out is equal to h nu and minus some w, and this w will be the work required to bring out the electron or eject out the electron from the surface. And why does it require some amount of work done here? And that is because that this electron is bound, it's not a free electron, it's bound to the atom and to the metal. So there are a lot of attractive interactions and attractive forces that bind it to the material, and that's why there will be a function, or this which is called as a work function, that is required for it to come out. Okay. So the K max according to him, that's the maximum energy of the electron, which is what we have discussed, is same as h nu minus, let's call it as a W0, which you often see as phi 0 in literature, or just phi, which is called as a work function, which is specific to a metal. It's a metal property. Okay. So the kinetic energy is actually h nu minus W0, and so it's a W0 is a work function. So either W0 or call it phi 0, call it phi. This is the work function. And as I said, it's a specific to the metal. So, so potassium, sodium will have different W0 or phi 0, and so on. So now if you equate this to the stopping potential, which is what we have done even in Hertz's original experiment, this is equal to h nu minus W0. So V0, which is the stopping potential, is h over E nu minus W0 over E, and this is the equation which Einstein obtained, and that clearly tells the Milikan's result, which you've seen just here, where you found that your potential is proportional to the frequency, and there is a stopping potential, or rather there is a stopping frequency, a critical frequency before, or rather below which there is no emission of photoelectrons. Okay. So this is so to say the wave property of light that is is being made clear, along with the fact that the classical theory of light, or the classical theory for the wave nature of light, is insufficient because it could not answer some of the abnormalities associated with the experimental results. Okay. The second thing that we want to look at is the Compton effect. Okay. And as I said earlier, that this shows the particle nature of light. Okay. It's again, this is slightly complicated for you, but I will just tell you the basic necessary details so that you understand it. So there is a source of X-ray. Okay. So this is source of X-ray, and I'm only schematically drawing it. Source of X-ray. So the X-rays come out, which means photons come out of certain wavelength and frequency, and there is a stationary scatterer. Okay. So this is a scatterer. It's stationary, which means that the electrons are stationary here. It could be a metal target and so on, and this one, the this photon comes, it strikes the electrons that are there in the scatterer. Now this is the scattered beam. Okay. And this scattered beam is made to impinge on a crystal. So this is source of X-ray, as I have written. This is the scatterer, which could be a metal target, and this is a crystal. And this is the most difficult part for you to understand, that this crystal is, it undergoes diffraction, or it shows diffraction phenomena for the X-ray, because the wavelength of the X-ray that matches somewhat closely with the spacing of the atoms or the ions in the crystal. Okay, and this is the way that we actually calculate the lattice spacing or the spacing between two adjacent planes, which are called as a Bragg plane, and there is a diffraction phenomena that goes on there, and this is basically how the crystallography, which is a part of solid state physics, everything that you see is a crystal, like the salt that you eat is a crystal called as the NaCl crystal. Okay, and for one to know what's the crystal structure, whether it's a simple cubic type or a body centered cubic or a face centered cubic, one needs to do an X-ray diffraction of that. So in our physics labs, we routinely do experiments using X-ray diffraction, and we have very high-end X-ray diffraction facility. That's besides the point. So what happens is that when this scattered beam that falls on a crystal, it and then from there it is being detected by a detector, we know that which wavelength. So this wavelength, information about the wavelength is available because of the crystal. Otherwise there is no point in keeping the crystal. Okay, the crystal only has a sort of work that it gives you information about the scattered X-ray. So this is the incident X-ray and there is a scattered X-ray. The scattered X-ray, which wavelength or what is the wavelength of the scattered X-ray, that is the most important thing that we need to know, and that's why this crystal is being put. We'll remove this because we'll draw a much simpler diagram in which we'll analyze this problem of Compton effect. This was done by Compton. When was it done? You can look at literature. It's done in 1923, the same year that Milikan did that. Milikan got a Nobel Prize in 1923 because of this photoelectric effect. So we'll change this picture to a much simpler one, but this is the schematic experimental diagram for this effect, Compton effect. Okay, so let's see that. The simplified picture is really simple. You really don't need to worry too much about that. So we have a photon coming in, and just showing it by a wavy line. Let's do it once again. And it goes and hits an electron. So we remove all these scatterer, etc., just an electron. So there is a photon which has so there's incident photon which has wavelength lambda and a momentum p0 and incident initial energy to be E0. The electron is at rest. Okay, and after it scatters, the photon goes in this direction, the electron goes in this direction, and if you take this horizontal initial direction of the photon, if you and then this angle is theta and this angle is phi. So this is the scattered electron, this is the scattered electron, this is the scattered photon. Will electron, we are just putting a circle with filling it up with hatched lines, and for the photon we simply denote it by wavy line. And so this has a wavelength lambda prime and an energy, call it E1, and a momentum P1. This one has an energy, kinetic energy K. Of course, there is no potential energy, kinetic energy K, and the momentum to be P. So the photon strikes a stationary electron. The photon gets scattered by an angle theta with respect to the original direction. The electron gets scattered with respect to the original direction by an angle phi. The electron has a no motion initially, so the initial energy of the electron is the rest mass energy, which you have learned in relativity. So we assume this scattering process as if there are two hard spheres scattering, just like what you have learned in your first course of mechanics, even before this coming to the college. In your school, you have learned scattering and apply momentum and energy conservations, and um, most of the time it's simplified by a lot of factors. Otherwise, a three-dimensional scattering is really a difficult problem because of the reason that there are three momentum components of momentum, that is px, py, pz, and energy. That's the four unknown variables. Even if you supply all the incident energies and momentum, but the number of unknowns will still be four. So most of the time, either we are given additional condition in order to solve the momentum energy conservation relation, or else we solve it in what's called as the center of mass frame. I'm sure that you have learned that as well. All right. So we'll apply momentum conservation here. So first, momentum conservation. Okay. So what's the momentum conservation? So this is equal to P0, that's the initial momentum of the photon. This is equal to P1 cos theta, that's the momentum of the photon, scattered photon, and there is a momentum of the electron, which is P cos phi. So this is equal to, so this is the initial direction, so you can take it to be the x direction and this to be the positive y direction. Okay. And similarly for the, let's call it as equation number 1a, and let's write for the y direction, it's P1 sine theta, it's equal to P sine phi. Okay, so this is for the conservation in the y direction. Okay, this is very simple. So if you square and combine, so square and add basically, so you have a P0 minus a P1 cos theta square equal to P square cos square phi, and P1 square sine square theta is equal to P square sine square phi, and simply add them. If you add them, the right hand side adds to just P square, and the left hand side you can do a little bit of simplification, which is P square plus P1 square minus 2P1 P0 P1 cos theta, which is equal to P square. So let's call this as 2A, 2B, and this equation, which is after you add them, you get an equation number 3. Okay, it's fairly simple. There's nothing much that we have done here. All right. Okay. So that's equation number 3 that you have there. So now conservation of energy. All right. And so this is equal to E0 plus m naught c square. Okay, because E0 is the energy of the incident photon. This is the rest mass of the electron, because the electron has no kinetic energy initially, and this is equal to E1, which is the energy of the photon, scattered photon, then the kinetic energy of the electron, and of course the rest mass energy will go together, which gets cancelled out eventually, which gives you a simple relation that E0 minus E1 is equal to K. That's let's call it as equation 4, and this is just a simple energy conservation equation, and we have assumed that it's an elastic collision, and that's why the momentum and energy both are conserved. In inelastic collisions, only momentum would be conserved, but here it's both of them are conserved. Now, um, the little bit of complication into the calculation is brought about because photons and electrons both are relativistic particles. They at least move with speeds which are comparable to that of the speed of light. Photons are of course light, but so the relativistic expression for energy is equal to E square equal to P square C square plus M square C4. So for a photon, m naught is equal to 0. E is equal to Pc for photon, but not for electron. Electron is a massive particle. Okay. So P is equal to E by C is equal to H nu by C. This is what we are using Planck's hypothesis and what even Einstein advocated in the context of photoelectric effect. So this is your equation number 5, and if you compare 4 and 5, then you get from 4 and 5 you get C P naught minus P1 is equal to K. So let's call that as equation 6. Let me write that. So now for the electron, the energy is so this for the electron. So it's K plus m naught C square. M naught is the rest mass of electron. So this square is equal to P square C square plus m naught square C4. That's the relativistic expression. And if you simplify it, uh, then you have K square equal to plus 2K m naught C square is equal to P square C square, and so K square by C square plus 2 m naught m k naught, sorry, m naught k equal to P square. So this is equation number 7. Okay, so that's for the electron. So if you put P square on the right hand side from equation 3, you've seen equation 3 there, and put so you put P square from equation 3 and K from equation 4. Okay, if you do that, then you get a lot of simplification, and this is P naught minus P1 square plus 2 m naught C P naught minus P1 equal to P naught square plus P1 square minus 2 P naught P1 cosine theta. And if you simplify it further, you have m naught C P naught minus P1 equal to P naught P1 1 minus cosine theta. It's a pretty simple calculation. I simply write 1 minus P1 by 1 minus P naught equal to 1 by m naught C 1 minus cosine theta, and if I multiply top and bottom, I mean not top and bottom, if I multiply both sides by h, then I have h here. So H over P1 according to de Broglie's theorem, that's equal to lambda 1, which is the um, the wavelength of the scattered photon, which we have written as lambda prime there. So we can call a lambda prime, and minus lambda. Did we call it lambda? We call it lambda. So lambda 1 minus lambda. So this is equal to h over m naught c. Uh, and 1 minus cos theta, and this h by m naught c is actually called as a Compton wavelength, and it must be having the dimension of length, because the left hand side is the dimension of length. So that tells us that there is an equation that we got, which is the difference in the wavelength. So what happens is that the photon strikes the stationary electron, it transfers some of the energy to it, which is expected, and in the process, the wavelength of the scattered photon, it changes from its initial value. So, which is what we have expressed as lambda prime minus lambda, or it's called delta lambda. So delta lambda is, you see, it's positive in the sense that because cos theta has a value which is maximum value is equal to 1, and minimum value is of course minus 1. So in any case, delta lambda, if you call this lambda prime minus lambda to be delta lambda, then we get a nice and simple relation that delta lambda equal to lambda c1 minus cos theta, and this is the Compton effect equation, or the equation governing Compton effect, where theta is the direction of the scattered photon with respect to the original direction of incidence, or the original propagation direction. So lambda c is the Compton wavelength, which has a certain value. Theta is a number, and if you have a grazing incidence that is almost no, if theta is equal to 0, say for example, which means that the photon, a scattered photon, does not deviate much, then this is equal to 1, and then delta lambda goes to 0, which means that there's no change in wavelength, or there's no change in energy of the scattered photon. And the maximum happens when cos theta is equal to pi, theta is equal to pi. So if theta is equal to pi, cos theta becomes equal to minus 1, and it becomes delta lambda is maximum, which is twice of lambda c. So if the scattered photon is bounced back in the direction of the incident photon, that's when the maximum change in energy happens, and maximum change in the wavelength happens. And so your h over, so this lambda c has a value. Let me erase some of these things. So lambda c is equal to h over m naught c, which is equal to 2.43 into 10 to the power minus 12 meter, which is nothing but 0.0243 angstrom. Okay, so you see that the characteristic length is so small that h becomes important. Okay, and that's why quantum mechanics become important. However, we have all used classical energy momentum conservation relation. So light shows up as really a particle in this experiment, and it once again enforces, and it's a perfectly nice example, which is and the experiment is done, and where one can actually plot your delta lambda to be a function of theta, and this one grows like this. Okay, so this is like pi and by 2, and this is like pi and so on and so forth. Okay. So this is experimentally verified, which means that all these calculations that we have done are perfectly fine. There is no problem with the calculations, and it also sort of says that light really shows up both the characters. Okay. All right. So since we know this, let me go to another topic which is very related, which are called as group and phase velocities. So let's write phase and group velocities. Uh, in order to understand what is this and why should we be talking about, let us understand, or rather imagine a situation that you are standing in a metro city, say Bombay, and you're standing on a high rise, and it's the time 5:30, say for example, in the evening, and it's the time that the office gets over, and people are going back to either catch their trains, and or they are going to take their buses, or somebody taking their own car and so on. So there's a stream of people moving towards, away from the office space. If you stand on the top of a tall building, you'll see that thing. And if you see that crowd moving, the crowd has a velocity. Okay. And if you take sort of a telescope and try to or rather sort of something, you want to look at one particular individual and want to understand whether he or she is in a hurry to get back earlier than others. If you see that, you'll be seeing that there are several people who are actually scurrying faster than others, and it probably doesn't affect the crowd velocity. The crowd would still be moving at that pace, whereas one or two people in the crowd have a sort of rush to get home, or someone doesn't maybe having a rush to go home at all and would be walking very slowly. So those individual persons would have a phase velocity, and the crowd has a group velocity. So that's the difference. So when we translate it into quantum mechanics, let's try to understand that what is the phase velocity of a single wave. Okay. And then we'll talk about group velocity for a group of waves, or rather a collection of single waves. Let's see it for one particular case. So let's write down a wave which is given by sine kx minus omega t. Okay, with some amplitude. It doesn't matter. I mean, it's not important. And I'm writing using a symbol which I'll be using very extensively throughout the later part of the course, which is called as a wave function. We are simply using it as a function now. It's a function of x and k, where k and omega, where k is equal to 2 pi over lambda is called as a wave vector, and lambda is the wavelength, and your omega is related to the energy, which is equal to, say for example, h cross omega. So this is how the energy and momentum are implied here. So if I see that when these things have if I want to find what is the velocity, what I'll do is that I'll put this equal to 0, or if you don't want to put it equal to 0, because I want to see the nodes, the point at which the function is vanishes. So this is equal to say I'll put it as a constant. So it doesn't have to be 0. So I just look at one point of the wave which moves at constant speed. Okay, and if that happens, then your x over t or x equal to some constant plus omega by some other constant basically. So let me write it as constant. So x over t, which is the, let's call it as a v phase, which is equal to omega by k, and this is called as the phase velocity of the wave. Okay, so this is the velocity with which each individual person would be moving in that crowd if you talk about one person. Okay, I mean, and there's a distribution of such phase velocities which will eventually make a group velocity. And how do we understand the group velocity? Let me take two such functions. Okay, let me take two such functions. Let's call it as, okay, I can write it here itself. All right, thank you. So psi of xt now is equal to psi 1 of xt and plus a psi 2 of xt. You don't have to take two, you can take many, but we are just for demonstration we have taken it as 2. So psi 1 is, say for example, sine of kx minus omega t, and psi 2 I can take it as k1 and k2, but instead what I do is that I take it as k plus dk x minus omega plus d omega t. So that's psi 2. Is that clear? So I've taken two functions, sinusoidal functions, two waves, because you know each particle has a wave representation. So I'm talking about either talking about two particles or two waves, and these two functions are simply like this: sine kx minus omega t, sine k plus dk into x, and omega plus d omega t, and so on. And then when I superpose this, I have told you earlier that the phenomenon of superposition holds, and because we have a linear system, and so this is psi 1 plus psi 2, I'll get a displacement or I'll get a wave. So this is equal to sine of kx minus omega t and plus sine of, well, write it below, sine of k plus dk x minus omega plus d omega t. And now we have to superpose them by using cosine of a plus cosine of, or here this is sine, sorry. So we have a sine function, so sine of a plus b and if you do that, then this becomes equal to 2 cosine a minus b by 2 sine a plus b by 2 and so on. So just your familiar trigonometry formula. So if you do that, your resultant psi is equal to 2 cosine dk by 2 x minus d omega by 2 t and sine kx minus omega t. Okay, so you see there's something interesting here. This is the wave that propagates, and there is an amplitude which modulates, which means that if you plot this thing, it will look like that it will have such uh, amplitudes being modulated, and there are these things which are inside. So this is that sine kx minus omega t and so on. So this sine function is enveloped by this cosine dk by 2 x minus d omega by 2 into t. So that limits the actual. So this is not a sine function. The sines are being chopped off at the boundary. Okay, and this is the envelope function. This is how the psi, it propagates as a function of x. And this envelope function has a velocity which is Vg, the group velocity, which is the velocity of the crowd. Now I have just taken two of such entities and have superposed them, and which is when if I put dk by 2 x minus d omega by 2 t to be equal to 0 or some constant value, which means that I want to see the same phase. That is what it takes to go from this point to this point, which are at the same phase. Or you can look at how much time it takes in order to come from this point to this point when there are nodes, and this will tell you is it what. So if you put it equal to 0, so your x by t, which is now equal to Vg, this is equal to d omega by dk. Okay, so there are two things that we have learned. The phase velocity is omega by k, and the group velocity is d omega by dk. Okay, this is quite important, and these are called as a group and the phase velocities. Okay, so let me give you an example, and I just have enough time for one small example. So let us see that your Vg, which is equal to d omega dk, which you can multiply it by h cross top and bottom. This will give you a dE dp, where E is the energy and P is the momentum. And if you try to calculate that, so if you have E equal to P square by 2m, then which is a non-relativistic formula, so a dE dP becomes equal to P by m, which in non-relativistic is equal to V. So that's the for a particle which may represent matter waves, is velocity is same as the group velocity. And if you take this in the relativistic case, which is equal to E square equal to P square C square plus m square C4 m naught square. So if you calculate dE dP, so this is equal to PC square over E, and if you use E equal to your familiar relativistic equations, so this for the relativistic particle is V square minus C square, and P is equal to mv divided by 1 minus V square minus C square. You again get it the Vg, which is equal to dE dP, again comes out to be V, which is true both in the non-relativistic and the relativistic case. In fact, if you're trying to find the for the non-relativistic case, if you try to find the phase velocity, it comes out as V by 2, and for the relativistic particle, try this. It comes out something unphysical. It comes out as C square by V, and C square by V is a quantity which is greater than C. So that's an unphysical result that you get. So this is about group and phase velocities, and we have shown experiments such as this Compton effect and photoelectric effect, and we have also discussed the the wave particle duality as put forward by de Broglie. Okay, we'll start with Schrodinger's equation and the solution. So first we'll talk about wave function and various things and operators and so on, and we'll also look at other problems related to Schrodinger's equation, how it is being solved for a given simple forms of potential is what we'll see.